You're listening to DTFHN for March 8, 2026. I'm your backwards compatible host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where the excuse in the thread is the point. Today has the weight of things built to last. Let's run it. 233 days, 71 consecutive commits. That's not a benchmark task. That's a relationship, and researchers just asked AI agents to show up for it. So is a new evaluation framework for something the field has quietly avoided measuring. Not can an agent write code that passes tests today, but can an agent maintain a codebase over time without quietly breaking everything it touched last month? 100 tasks, each rooted in the actual evolution history of real repositories. The agent isn't just solving a ticket. It's inheriting a living system and being judged on whether it leaves that system healthier than it found it. The benchmark uses continuous integration as the signal. CI doesn't care about your intentions. It runs, it passes, it fails. What makes this design sharp is that it catches regressions. The silent killers. You fix a bug in Module A, and 3 weeks of commit history later, Module B quietly stops working. Humans catch this because they remember. They built the thing. They carry context across time. Agents don't, or haven't, and the results here are clarifying in that particular way bad news sometimes is. Recent models show real improvement on the tasks themselves, while also showing regression rates that are, by the paper's own framing, pretty rough across the board. The capability is developing unevenly. They're getting better at the sprint and worse at the marathon, or more precisely, better at the task, still struggling with the consequences of the task. The HN thread has someone pointing out that long-term maintainability is exactly what separates humans from agents in daily use. That's the practical version of what this paper is measuring. Not does it work, but does it still work after the next 70 commits? Run this forward. The benchmark itself is on ArcSci. The methodology is public. Anyone building an agent-assisted development pipeline can use this to pressure test their system against something that actually resembles the job. That's what good evaluation infrastructure does. It gives the whole field a shared definition of what works means. 100 tasks drawn from real repositories, measured against real CI, with regression tracking baked in. The tools exist. The evaluation framework is available. Now we find out which architectures actually hold up. From software correctness to raw compute is... Story 2 is about which cloud VMs actually deliver on their promises in 2026. Picture the pitch meeting. Somewhere in 2019, a VP of infrastructure stands up and says, "Rent your compute, pay only for what you use, no capital expenditure, pure operational efficiency." The room nods, the CFO nods. The slide deck is beautiful. 7 years later, a commenter on a Cloud VM benchmark post writes, "Still having your own hardware seems so much cheaper." The benchmark itself is thorough. 40 VM types across 7 providers, tested across multiple regions because, and this is the part worth pausing on, not all instances are created equal even within the same provider. The same VM family can deliver meaningfully different performance, depending on which data center you land in. You are not buying a spec sheet, you are buying a lottery ticket with good odds. The technical finding that dominates 2026, AMD ePike to Ren. The generational leap from Genoa to Turin is significant enough that one commenter ran their full CI suite on GCP's Turin-backed instances and found the results insane. Another noted that Turin's per-core performance is now competitive with consumer desktop silicon. The SWE-CI, an enthusiast gaming chip, sits in the same performance tier as cloud instances costing real money per hour. The gap between server CPU and what you can buy at a computer store has nearly closed. Here's where the bootstrapism math gets uncomfortable. Cloud compute democratizes access to hardware you couldn't otherwise afford. That's real. A solo developer in Lagos can rent a 96-core Turin instance for an afternoon and run a workload that would have required a data center contract 5 years ago. The latter is genuinely lower. But the price per performance comparison in this benchmark tells a parallel story. If your workload runs continuously, the on-demand pricing model stops looking like flexibility and starts looking like a subscription to someone else's appreciation schedule. The commenter who noted, "Every big corporate I have worked at has lower cost of capital than Amazon," is doing the arithmetic correctly. The benchmark is public. The methodology is documented. The data covers single-thread and multi-thread performance, regional variance, committed pricing versus on-demand. Someone with a consistent, predictable workload can use this to answer a genuinely important question. Are you renting because it's strategically flexible? Or because the pitch meeting was convincing? AMD Turing dominates. The tools to evaluate whether you actually need it are now freely available. Both of those facts are worth knowing. Story 3 is a hard left turn, pause away from benchmarks and procurement cycles, into someone building a 6-inch Newtonian reflector with their own hands. One comment buried in this thread stopped me cold. Someone writes, "My father built an 8-inch Newton. We moved to a new house. It needs a new mount, no fanfare, no context. Just a telescope that outlasted a household, waiting to be rebuilt." That's the undercurrent running through this entire PARI jet. Instruments made by hand carry something that purchased ones don't. The build itself is called Curiosity, a 6-inch Newtonian reflector, PVC tube from a hardware store, spider vanes machined from a 30-centimeter ruler. The kind you'd find at a stationery counter for pocket change, primary mirror housing in 3D printed components, Velcro holding the optic to its backing with rubber padding for compliance. The whole thing designed in Fusion 360 and documented with enough rigor that you could replicate it. Now strip it to first principles. What does a telescope actually require? A primary mirror with the right focal length, a secondary mirror positioned precisely to redirect the focal cone to an eyepiece, a tube long enough to block stray light, wide enough to not vignette the beam, a focuser. That is the complete list. Everything else, the carbon fiber tubes, the machined aluminum cells, the 5-figure price tags, is refinement on top of a surprisingly simple optical system. The calculation at the heart of this project is almost elegant in its plainness. Focal length minus tube diameter minus focuser height minus a small correction factor equals where your diagonal goes. 900 millimeters minus 95 minus 96 minus 25, 684 millimeters. The geometry of starlight reduced to arithmetic you can do on paper. What makes it craft, rather than just construction, is the thinking visible in the decisions, the 190 millimeter inner diameter. Not arbitrary, derived from the mirror size plus a 20 millimeter offset on each side to keep fasteners clear of the optical path, the Velcro attachment. A deliberate choice to allow adjustment without adhesive permanence. The spider vane design linked to 3 separate references on diffraction spikes, because someone cared about the quality of the image, not just the existence of the image. The tools exist. Fusion 360 has a student license. Mirrors are available from optic suppliers. PVC pipe is in every hardware store. A 30-centimeter ruler is 99 cents. Someone's father built an 8-inch telescope by hand. Now someone else is building a 6-inch, and publishing every dimension. The knowledge stays in circulation. Moving on. The strongest argument against Rust-based WebAssembly is not the learning curve, it's the asymmetry. You're managing two memory models simultaneously. JavaScript's garbage collected, reentrant, async runtime on one side, Rust's strict ownership and borrowing rules on the other. The boundary between them is a table of opaque pointers. WASM tries to paper over this gap with generated glue. And critics are not wrong that it both under and overfits. Some safe patterns get rejected. Some genuine footguns get happily accepted. A competent engineer surveys this and decides the complexity cost exceeds the benefit. Use something else. That argument is precise. It's also incomplete. What it misses is that the complexity isn't irreducible. It's underdocumented. Brooklyn Zelenka's notes on Writing WASM are exactly the kind of artifact that changes the calculus. Not a library, not a framework. A set of naming conventions and boundary-crossing patterns, learned through friction, published without ceremony. The substance is worth walking through. Pass values by reference across the WASM boundary, rather than by value. The ownership semantics are cleaner, and you avoid a class of footguns. Prefer RC over mutable references for anything that needs to live on the WASM side and be accessible from JS. The reentrant nature of JavaScript makes alias mutable borrows a trap. Don't derive copy on exported types. Prefix Rust exported structs with WASM. Set the JS name to the unprefixed form. Prefix JS imported types with JS. The naming discipline sounds pedantic until you're 3 layers deep in a callback, and you need to know immediately which side of the boundary a type lives on. The compiler enforces Rust rules on the Rust side. It cannot enforce them across an ABI boundary into a garbage-collected runtime. That's not a bug in the design. It's a physical constraint. The naming conventions are the human-readable encoding of that constraint. Here's the understated part. Excellent programmers have fought badly with WASM. Zelenka names this directly. The patterns in this post aren't obvious. They were discovered through accumulated pain and documented so the next person doesn't have to rediscover them. The tools exist. The patterns are now written down. Someone put them where you can reach them. That's the whole story. The tools exist and the patterns are written down until they're not. Story 5. What does it mean for a piece of software to be unmaintained? The question isn't semantic. It has real consequences. When UV Astral's Python package manager added a warning labeling PyPy as unmaintained, a core PyPy developer showed up in the thread to correct the REH code. The project isn't abandoned. It's under-resourced. Those are different things, and the difference matters more than the PR discussion suggests. The analogy I keep returning to is cathedral maintenance. The great medieval cathedrals of Europe weren't built by teams that could keep pace with every new construction standard. They were built by small groups of specialists, sometimes working across generations, with deep mastery of a specific craft. When funding dried up, work slowed. The cathedral didn't become unmaintained. It became stressed. That distinction matters because unmaintained signals, "Don't touch this. Stay away. It's compromised." Under-resourced signals, "This needs help." PyPy is a cathedral. It took decades of volunteer work to build a JIT-compiled Python implementation that runs in many common workloads. 5 to 7 times faster than CPython. Microsoft's faster CPython team, with actual salaries and corporate backing, spent 4 years chasing a 5 times goal and achieved roughly 1.5 times. PyPy has been doing better than that on donations and weekend hours. That's an extraordinary technical achievement. and it deserves to be named as one. The remaining core developers are clear. They fix bugs, they improve the JIT, they care. What they cannot do is match CPython's release cadence with the resources they have. That's a funding problem. The label unmaintained in a package manager carries weight. It changes behavior at scale. Projects stop targeting PyPy. Maintainers drop it from their test matrices. Users don't install it. The warning becomes self-fulfilling. A slow erosion shaped by a single word choice. There's a harder question underneath this. The faster CPython effort happened inside Microsoft, behind salaries and roadmaps. PyPy happened in the open, built by people who believed a faster Python was worth their evenings and weekends. If it doesn't survive, it won't be because the approach failed. It'll be because sustaining serious infrastructure work on goodwill alone has limits. The PyPy team put their contact page in the thread. If you use Python, especially for anything compute-intensive, that link is worth 2 minutes of your attention. What if running your own language model was just as accessible as contributing to an open runtime? Story 6. In your one you boing drain, what you comps do, something workstation costs 30,000 alls and required dedicated cooling infrastructure. It ran Unix, handled floating point math faster than anything you could put on a desk, and was considered a specialist tool. Something universities bought, labs shared, researchers scheduled time on. 12 years later, a $2,000 consumer PC running Linux matched it on most benchmarks. The threshold crossed so quietly that most people didn't notice until after Qwen 3.5. Feels like that kind of crossing. Alibaba just released a model family. The Thunderful B, ASM B, Punji B, and their smaller siblings. That runs on a 22 GB Mac, a laptop, machine you bought to edit video and check email. And it's not running in degraded mode, apologizing for its constraints. The 35B A3B variant hits around 100 tokens per second on a consumer GPU. That's faster than most cloud inference endpoints served you last year. The engineering that makes this possible is worth sitting with. The 35B dual A3B is a mixture of experts' architecture. 32 billion total parameters, but only 3 billion active on any given token. The model carries the knowledge of something much larger, activates the relevant slice, and runs with the footprint of something much smaller. At full bit quantization, with unslothed approach. Critical layers upcasted to 8 or 16-bit rather than uniformly compressed. You're getting 22 gigabytes of runtime cost for a model that benchmarks above things that required data center hardware 3 years ago. 200,000 homologation 100. 201 languages, hybrid thinking mode. Toggled the reasoning chain on for hard problems, off when you need speed, and the whole family is available right now through Unsloth-free, loading in llama.cpp, running on hardware sitting in people's home offices. There's a comment from someone running the 9B on an RTX 4070. Outperforms the majority of online LLM services. That sentence deserves a moment. Not because it's hyperbole, because it's probably accurate, and because 18 months ago it would have seemed optimistic. The Sun 1 crossed from institutional to personal, not through a press release, but because the math eventually forced it. Enough transistors, cheap enough, and the threshold falls. We are watching that happen again, in real time, 1 GGUF download at a time. And if open technology democratizes intelligence, here's what that intelligence goes on to find Pause Story 7. Every machine learning system I've worked with has the same failure mode. It learns the distribution of its training data, not the underlying truth. Feed it enough authenticated Rembrandts, and it learns to recognize Rembrandt. But the authenticated Rembrandts were authenticated by people who might have been wrong. The error propagates silently. The Rijksmuseum just ran a correction. Vision of Zacharias in the temple painted at WZM 633, sitting in a private collection for who knows how long, just got reclassified. Not a follower of Rembrandt, not a workshop attribution. Rembrandt van Rijn, the same methods they used on Night Watch. Macro X-ray fluorescence, infrared reflectography, microscopic paint analysis. Turned on the smaller, quieter work, and the evidence came back unambiguous. Here's the question nobody in the press release wants to engage. How many others are wrong in the other direction? The Rembrandt research project spent decades systematically de-attributing paintings. Hundreds of works that auction houses and collectors had banked on, scholars had built careers on, museums had insured at staggering valuations. Quietly reclassified, the market moved, careers adjusted. Nobody held a press conference about that. Attribution in art has always been partly scientific, partly consensus, and partly economic. When a painting is owned by a private collector and sits off the market, there's less pressure to get the answer right. When it goes up for auction, suddenly everyone finds the resources for a thorough examination. That's the sarcasm in this story, if you want it. But there's a better angle. The Rijksmuseum didn't just publish the conclusion, they published the data. High-resolution scans, publicly downloadable. The methodology from Operation Night Watch, the most technically sophisticated painting restoration and analysis project in history, is now being applied to the broader canon. And the results are being shared. One commenter clocked it immediately. Better than most museums who treat their scans like proprietary assets. A private collector owns the canvas. The knowledge is public now. That's the correct shape for how expertise should flow. Tools doing real work, outputs released into the commons, the answer belonging to everyone. The painting goes on view March 4th. Go see it if you're in Amsterdam. Download the scan if you're not. The 391-year-old question has an answer. Color and knowledge, two things that belong to everyone. Story 8 takes us into color science, pause, specifically why your screen is lying to you and what to do about it. The number is Damery is point Damer of 4045. It appears in the gamma correction formula, and most people treat it as a magic constant. Copy it from the article, paste it into the code, move on. But run that number back to its source and you find something funny. That threshold exists because of cathode ray tubes, specifically because of how CRT phosphors responded nonlinearly to electron beam intensity, the gamma curve. The top 0.4 exponent, the 12.92 divisor, is the mathematical residue of a display technology that became commercially obsolete around 2007. sRGB was standardized in 1996 by HP and Microsoft. It baked in the CRT response curve because that was the hardware everyone had. It also baked in D65 as the reference white. Lutz sounds 40 Helva Kelvin, which is a mathematical model of daylight filtered through an overcast northern European sky. That's what neutral means in this standard. Every color calibration you've ever done on a screen. Every true white display certification. Every color accurate monitor review. Secretly anchored to the average light of a cloudy day somewhere over Amsterdam. Now run this forward 5 years. Every image model trained in the last decade ingested its data as sRGB values, not lab values, not linear light, gamma compressed, CRT corrected, Northern European daylight normalized pixels. The networks learned color relationships in a space that was never designed to model human perception. It was designed to drive a phosphor gun. The unintended consequence: when you generate an image, upscale an image, or run any color-sensitive operation through one of these models, you are working through the ghost of a display standard that made complete sense in 1996 and has been load-bearing infrastructure ever since. This is what Lab was built to fix. The perceptual uniformity point is the thing. A delta E of 1 means human eyes cannot detect the difference. The map: normalize, gamma expand, matrix, multiply into XYZ, then fold into lab. It is verbose, but it connects pixel values to something real, the actual distance between colors as your visual cortex processes them. That connection matters whenever you're comparing images, matching colors across devices, or asking whether two shades are genuinely different or just arithmetically different. One commenter linked to OKLab, Bjørn Ottoson's 2020 refinement. Simpler to implement, better hue linearity, fewer edge case failures. One developer, one blog post. Publicly available, the CIE published their standard in 1976. The better version took 44 years, required no committee, and fits in a README. The tools exist. They've been sitting there. Moving on! Pokemon Red runs on geometric constructions from 300 BCE. That's the sentence. That's the whole thing. Here's what that actually means. A developer named 0x0mare built CasNum, compass and street edge number, a library that represents every number as a point on a plane and implements arithmetic the way Euclid did, intersecting lines, bisecting angles, constructing circles. Addition is a midpoint doubled. Multiplication is triangle similarity. Messier, but they work. The entire thing bottoms out on 5 primitives. Draw a line, draw a circle, find where they meet. That's the ISA. Then they wired it into a Game Boy emulator. Follow this principle to its limit. If compass and straight edge constructions can represent any constructible number, and if all computer arithmetic is ultimately just numbers, then, in theory, you could implement every ALU opcode geometrically, which is true, which they did. The only file they had to touch in PyBoy was opcodestrine.py, one file. The ancient Greeks are now, technically, running an 8-bit processor. What I find genuinely beautiful here is the layering. The bottom layer is pure geometry. No numbers, just points and intersection. On top of that sits arbitrary precision arithmetic, built from geometric primitives. On top of that sits RSA encryption, fully functional. On top of that sits a Game Boy CPU, each opcode expressed as a sequence of constructions. And on top of that runs 2048, freely distributable. Or, if you have it, Pokemon Red. Every frame rendered is the outcome of thousands of geometric constructions, cascading down through layers of abstraction that shouldn't work, but do because mathematics is deeply, stubbornly consistent, regardless of how absurd your implementation choices are. The project includes a viewer that shows you the constructions as they happen. The circle.py formula for 2 circle intersections is over 3,600 characters. Because it resolves to a 4th-degree equation that Wolfram Alpha had to help crack. The author notes, "Good thing we have Wolfram Alpha. The ancient Greeks, notably, did not." One commenter wrote, "Think of these as your ISA. Yes, exactly. That framing does real work. Every computing abstraction, from transistors to opcodes to arithmetic to software, it's just a cleaner vocabulary built on top of a messier one. CasNum makes that visible by choosing the messiest possible vocabulary and building anyway. The README closes with, apparently one cannot square the circle using a compass and a straight edge, but at least one can run Pokemon Red. That's not a joke, that's a thesis. From building on the messiest possible vocabulary to building on the most ubiquitous one, pause, story 10. Docker turns 10. The fundamental problem is library conflicts. Linux boots from a single shared file system. Every process on the machine reads from the same lib, the same SWE-EF's application A. Needs lib SL 1.0. And application B needs lib SL 3.0. One of them loses. This is not a packaging problem. It is a namespace problem. The primitives to solve it existed for decades before Docker. Gatter, root, landed in Unix v7 in 1978. Give a process a different file system root. Linux namespaces separated PID spaces, network interfaces, mount points. C groups, contributed by Google in 2008, capped CPU and memory per process group. Union file systems let you layer reads. Write a change on top. Read through the stack. Every building block was already in the kernel. What Docker built in 2013 at PyCon was a user experience, a composition layer that assembled CRUD, namespaces, C groups, and union file systems into write a Docker file, run Docker build, run Docker run. The underlying kernel primitives did not change. The friction did. 3.4 million Docker files in public GitHub repositories. That number is the measure of what happens when you reduce friction on a correct abstraction. Now apply the open-close test, because this story earns it. The OCI, Open Container Initiative, standardized both the image format and the runtime specification. Containerd and Runc are the actual execution layer now. Docker, the company, is upstream of that, not in control of it. Someone repurposed Slark, a utilized dial-up networking tool originally built for Palm Pilot, to handle container networking on rootless setups without triggering corporate firewall restrictions. That is not a company building a moat. That is a commons being actively maintained by people who needed it to work. The architecture enforced openness in a way that mattered. When Docker Inc. experimented with licensing changes, the ecosystem did not fragment. Get routed around the changes because the image format was already standardized and the runtime was already a separate project. The objective function of the company could shift. The objective function of the technology could not, because the technology was distributed across too many hands. One commenter put the whole decade into a single sentence. We took the "it works on my machine" excuse and turned it into the industry standard architecture. Then we'll ship your machine to production. That is not a joke. That is a precise description of what reproducibility as infrastructure actually looks like. The decade of work was not building containers. It was building consensus around a format stable enough to become invisible. The format is now infrastructure. And because it runs on open specs, on kernel primitives nobody owns, on a commons that routes around capture. The next decade builds on something that holds. That is how open source wins quietly. This has been your daily tech feed for Hacker News for March 8, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Claude over Qwen 3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that outlasts the tools you use to make it. We'll see you back here tomorrow.